The next keynote speaker is Mohammed Atiquzzaman, known as Atik to friends, and Atik comes from the United States as well. He has a very impressive bio, so I tell you a few words while he is setting up. Atik graduated with degrees from University of Manchester in the UK, and currently he holds a professorship at University of Oklahoma. What he didn't mention in this, but he told me yesterday he was also in Australia, but I don't know why he is not saying this in his bio. Okay, so this is a kind of starting negative point. Atik is editor-in-chief of a couple of important journals. He is also on the editorial boards of a number of other journals. You can perhaps look at the conference website to get the details. He is a recipient of multiple prizes, including IEEE Communication Society's Freud LFC Prize. He is co-author of about 270 publications, including the book Performance of TCP/IP over ATM Networks. And he's going to talk to us. Really, we are moving from down-to-earth software engineering problems. We are moving to outer space, I suppose. We are moving from the cloud to the cosmos. And he will talk about extending the internet to space. There are two microphones. You can have one.
Thank you.
And the floor is yours.
I think, thank you very much for the introduction. What he didn't say is what White was saying, why he's here. Why I'm here, because I've never been to Poland before. So it's a very exciting place to be in. All right, so my talk is about extending the internet to space. We are familiar with the internet, which is the terrestrial internet, and this is a project which I've been working with the NASA, which is the space organization in the US. I think you have a similar space organization in Poland probably. Actually, there's a European one called European Space Agency, so that's a counterpart of the European Space Agency. So my talk is basically revolves around what I've been doing with them in a couple of projects. So the types of satellites, so NASA's basically objective is there are two main objectives. One is to look up into the space, and that's for space exploration. Another is to look down at the Earth. That's mainly for doing something good for the people on Earth, like weather prediction and all sorts of observations. So there are two objectives. And for these, they basically use spacecrafts, which are satellites basically, to do these two missions, or the two objectives. So what are the types of satellites? There are many types based on altitude. They're low Earth orbiting, which are very close to the Earth. They are orbiting the Earth. There is medium Earth orbiting, which is slightly higher up, and they are also orbiting around the Earth. And the geostationary ones, which are much higher up, they are also orbiting, but with respect to the Earth, they are stationary. So as the Earth rotates, those satellites rotate at the same speed. So if you look up in the sky, those satellites appear to be stationary. But those other satellites, they actually, if you look up, and if you can see a satellite which you can't, you'll see that they're flying by. So that's the three different types of satellites. And the type of satellites used for communication mostly, what we're going to look at is the low Earth orbiting, the LEO satellites. Because they're closer to Earth, their propagation delay is less, and there are other reasons why we use LEO satellites. All right, so here is an example of if you look at the satellites, what they look like in the sky. So that's our Earth. I don't know whether you can see it on here or not, but. So those are the low Earth orbiting satellites. They keep on rotating around the Earth, and at certain times they have a footprint on your place where you are. But you can see that these satellites are moving, so they lose connection with you, and the new satellites come in, and they get connected to you. So if you are in a place, you will find that these different satellites are coming and going away, and you have to continuously maintain connection with them. unless you are using a geosatellite, which is stationary. And most of them are LEO satellites for communication, and you have to continuously maintain a connection. That's where all this project comes from. So coming to the original topic, the topic is about connecting the internet to space. And if you are connecting the internet, one of the issues is the handoff, the mobility management. So if you are, for example, working with your phone or working with your laptop and you're moving around, you have to continuously hand off from tower to tower. So that's one of the issues. So when you are handing off from tower to tower, let's look at a cell phone and you're moving around. So you have to continuously hand off from tower to tower, and someone somewhere has to keep track of where you are. For example, when I'm here, people, when they're calling my US number, that's being forwarded to here. So the way it works is basically when I come here, switch on my phone registers with the tower, which is a local tower. And the local tower actually tells my home, that my home network, that I'm here. So when somebody calls my number in Oklahoma, that call is forwarded to here. That's how it works. So it's basically a forwarding mechanism. But in order to do this forwarding mechanism, there is this mobility management, how we manage the mobility. And the second issue is the handoff. When you are driving on the highways, you are continuously being handed off from one tower to another tower. So that's a handoff issue. So one is handoff, another is mobility management. How do they know where you are? So if you look at the satellite network, if you extend this sort of mobility to the satellite network, the space, there are different types of handoff that happen in space. In the terrestrial environment, if you are driving and if you have a cell phone, the sort of handoff that happens is between towers. That's all that happens. And the mobility management is to keep track of where you are. So those are two different issues. So in the satellite environment, there are different types of handoff. One is the inter-satellite handoff, because you can be handed off between satellites. There's a link handoff. That means I'll show you some examples of these. And then there is spot beam handoff. And then there is this network layer handoff. So if you look at the communication networking protocol, there is this link layer, which is lower down. And then there is this network layer, which is slightly higher up. So in the network layer, there are two types of handoffs you can see when the satellite works as a router, or the second type is the satellite is working as a mobile host. And I'm going to give examples of these. So here is an example of inter-satellite handoff. This is a ground station. So when satellites are up in the sky, they communicate to the ground station to download the data. That's standard procedure. So let's say in this particular case, there is this ground station and this LEO satellite is connected to the ground station. And since they're moving, so it is going to go away, and it will and another one will come up, and it will connect to the ground station. So that's how you communicate with satellites. So if you are communicating through this ground station, then you have to re-establish this connection. So it is very similar. If you look at these ones as mobile hosts, then you have to continuously keep on connecting this ground station to this satellite, which has all the data. So that is the inter-satellite handoff that you are handing off between two satellites. So ground station is handing off between these two satellites. Then there is link layer handoff. So this is a constellation that satellites usually go around the Earth in orbits. So there are different orbits, and these are some small satellites. So at a particular instant of time, at a particular snapshot, this might look like this, that these are satellites, and this is close to this one, this is close to this one. So if you want, you can establish a communication between these two, but this one and this one is probably too far away, or this one and this one is too far away, and you can't establish a communication because they're too far away. So when you communicate between satellites, usually you communicate with the one which is closest. And since these ones are moving, if you look at the next snapshot, you will find that this has moved to another position, this has moved to another position. So now you have to connect from this to this. So you have to do a handoff between the satellites. So that's another type of handoff you need to do, which is called the link layer handoff. Then the other type of handoff that happens is called the spot beam handoff. So when there is satellite here, it has a coverage area, or called the footprint, under which this area is covered under this satellite. And in order to use or reuse the frequencies, they are divided into, the footprint is divided into spot beams. So there are certain regions, and you use one frequency here, and you use a different frequency here. So these are called spot beams. And if the ground station is here, it is under this spot beam. And as you can see, if this satellite moves, the ground station comes in contact with a different spot beam. So you have to actually hand off from this spot beam which was here to this one. And there's a difference in frequency between this and this, the frequency at which it communicates. So you have to do a handoff from this spot beam to this spot beam. When I say you, it's the ground station which has to hand off. So there is a spot beam handoff. So the stuff I'm trying to establish is there's a lot of handoff going on in a satellite environment. And there are different types of handoff going on. So it's much more complicated in one sense that different types of handoff going on. It's much more complicated than the terrestrial environment where there is basically you are communicating between towers, so you just hand off between towers. So it's much simpler than this one. But the advantage of this type of handoff is it is deterministic, that you know exactly when the satellite will be over your ground station, so you can prepare the handoff. In terrestrial environment, you never know where the people are going to, which tower they are going to connect next. So it's a much harder problem. So in this case, that is a slightly easier problem, that you know which one you have to connect next, so you can actually prepare for it. So other types of handoff that happens is the network layer handoff. So in this particular case, there is a person here who is sitting somewhere where there is no internet connection. When I mean internet, there is no cellular connection or there is no Wi-Fi. Let's say in the middle of the ocean or somewhere in the mountains. And this person has to communicate using satellites, of course, because there is no cellular connection or Wi-Fi. So in this particular case, I'm trying to find which button it is. Okay. This person establishes a communication with the satellite, and then transmits data to the satellite. The satellite basically sends it to the ground station, and from there it goes to the internet, to the terrestrial network. That's how it is. That's how this person communicates. But this satellite is going to move away, and this person has to re-establish the connection with a different satellite. So there's a handoff going on there. In this particular case, the satellite is working as a router, basically taking the data from this person and routing it to the terrestrial internet. So this is basically a router. But the situation is there needs to be handoff from this satellite to this satellite. In the other scenario, the satellite can be like a mobile host. This is the sort of application which we have been working on. So, the space agencies, they collect a lot of data looking down into the Earth, and these data are collected by instruments which are on the satellites. Now those data have to be downloaded down to Earth, and the way they download it is very traditional. They connect with the ground station and download the data. But these satellites are connecting to the ground station, and during the period when they can see the ground station is very small. It's somewhere between 10 to 15 minutes, and then the satellite flies away and it loses connection with the ground station. So what it has to do is it has to wait until it gets gets in touch with the next ground station. And these ground stations are not frequent. I mean, when you are moving around, you hardly see the ground station. So these ground stations are not very, very common. So during that time, when it is not in touch with the ground station, it buffers all the data and then downloads all the data when it comes in contact with the new ground station. So that's a traditional method of data collection and downloading. So in this particular case, the satellite works as a mobile host. That means it has all the data to be downloaded. So here is a satellite here, and there's a scientist sitting here who wants data from this satellite. For example, the weather data or the agriculture data or the disaster data. There's a fire or earthquake somewhere, and you want the data immediately from the satellite. So this person wants to access the satellite. So the way it works is the satellite gets in touch with a ground station and downloads the data, which comes to a central server, and the scientist gets the data from the central server. That's how it works nowadays. And then the satellite moves away. It gets in touch with a different ground station, if it can find one, and then downloads the data. So during this period, although this diagram doesn't show, but there is some intermediate time when there is no connection. So this person has to wait for the data until this gets in touch with a new ground station, which could be hours. So this sort of case, we call it the satellite is working as a mobile host, in the sense that this is like our if you compare it like a laptop or a telephone, which is connecting between different ground stations or different towers. So that's the sort of thing we have, except that in a terrestrial environment, we are never without connection. When we hand off from one tower to another tower, it's seamless. You don't even feel that it's handing off between towers. It's continuous because the towers are very close, but the ground stations are not very close. So there is a period of disconnection. There's a long period of disconnection. So in this particular case, the satellite is working as a mobile host. So the question is, how do we manage? So I've just described to you lots of examples of handoffs in the space environment. Now, whenever there are different types of handoff, how do we manage the mobility? Because these satellites are all over the space. How do you manage the mobility? So the question is, at one time, before I tell you the question, at one time, when the government had a lot of money, they used to, or NASA or the other federal agencies, they used to develop their own applications. So if they required something, they would develop their own application from scratch. But that requires a lot of money. So the current thrust is to see if there is a problem, they try to see whether there is a solution existing in the terrestrial environment. If there is a solution, can it be adapted to our environment? That's what they are trying to do. This saves a lot of money because a lot of money has already been invested in, for example, in this particular case, mobility management or handoff, which is done in the terrestrial environment. So can we take that knowledge or those techniques and adapt it to the space? That could save us a lot of money because a lot of groundwork has already been done. So in order to do this sort of mobility management, of course, NASA was looking at what exists already in the terrestrial environment. In order to manage host mobility in the terrestrial environment, the protocol which is used is called mobile IP. And the mobile IP is, how many of you have heard about mobile IP? Okay, so I'm going to describe a bit about mobile IP. The way the mobile IP works is very much like the postal system forwarding of the mail. So if you live at address at a certain place, and if you move to another house, you change home. I don't know what you do here, but in the US what you do is you tell your post office that here is a new address. So all the mail coming to my old address should be forwarded to here. That's what is done. In the email system, that's what you do is you have a server at Outlook or whatever your workplace, and you can actually set up a forwarding to Gmail. So any mail coming to your work address is forwarded to Gmail. That's how it is. But how do you do it? Because you tell your workplace that I am going to check my email at Gmail, so please forward it there. And mobile IP is very similar in the sense that, the postal system. So when you tell the postal system, your home postal or post office, that this is my new address, please forward all the mail there. And they're going to forward it for a certain time, 3 months or 6 months, and then of course they will stop forwarding because it costs money to forward. So if someone wants to communicate with you, so this has also been used in the computer networks, and the scheme is called mobile IP. The reason it's called mobile IP is when you connect to a network, you get an IP address from there. If you move to a different network, you open your computer, you get a different IP address. So what we would like to do is, if I'm getting IP address which is different all the time, then how do I tell people what is my IP address? Right? If people want to communicate, the only identity I have is by IP address. Other than that, people cannot communicate with me. So how do I communicate with people? You might say that, I can do the communication nowadays. What's the problem? The problem is, whenever you go to a new place and you get a new IP address, you start a new communication. For example, Skype or email or whatever it is, you get a new IP address and you log on into the server with a new IP address, so the server knows where you are. But if you want to do a continuous mobility, you need something like one address which you can carry around. And this is called mobile IP because you are carrying the IP address with you. So when I'm at my university in Oklahoma, I have an address there, IP address, and it will be a static address. And I want to take that address when I'm in Poland. So I'm in Poland, I will give my IP address to everybody else. Everybody else knows my IP address. And this is the University of Oklahoma IP address. So what I'm going to do is, people will send me packets at the same IP address in Oklahoma, I will tell Oklahoma network that when there is a packet coming to my IP address, please forward it to Łódź here. Here is my IP address here. And they will forward the packet here. So that's basically a packet forwarding mechanism, which is followed by the post office. So what happens is there is a correspondent node which wants to communicate with you. You are initially at your home network, and this is your home agent, which is, so the packets from a correspondent node comes to your network, and then the network delivers it to you when you are in your home network. When you have moved away to a foreign network, a visiting network, then what you do is you communicate with you get to communicate with the tower or the Wi-Fi, whatever it is, get an IP address, tell the server that you are here and your IP address is this, but you don't belong to this network, you're a visitor. As soon as you tell this server you're a visitor, the foreign agent, which is the server here, is my foreign agent. That foreign agent is going to tell my server that one of your laptops or one of your nodes is actually with me. So if you receive any packet which has an IP address, whatever the IP address is, my home IP address, please forward it to here, and I can deliver it to your computer. So that's how it works. So so everybody sends packets to me at my home address, which is my permanent IP address, and that gets forwarded to here, which I get eventually. So that's the protocol which is called mobile IP. The reason being, I take my IP address along with me everywhere, and wherever I go, I get a new IP address, which is called the which is called the care of address, because I'm at the care of some other network. So there are two IP addresses I have here now. One is called the home address, another is called the care of address. So that's how the mobile IP works. Now we want to extend this to the space, because this has been working pretty well in the terrestrial environment. Now you might say, I don't use it, right? When you've been talking about mobile IP and all this stuff, and I can move around and I don't use it, or why do I use it? Actually, in order to use it, it's not very popular yet. There are some issues. That's why it's not very popular. The technology is mature, everything is fine, everything works. There are some issues that needs to be taken care of. One of them is you need to modify the internet infrastructure. How do you modify it? I need to have a foreign agent here whom I can tell that I am here. Can you tell my home agent that I am here? So you need a foreign agent and a home agent. So if I want to do this, I need a foreign agent. And not too many people are using this service, which means that they don't have this foreign agent. Sorry. So not too many networks have this foreign agent or home agent. Why is that? Because the sort of applications we run, we don't really need a seamless application. We are doing web browsing. So we do web browsing here. When we move to a different one, we get a new IP address, and we do web browsing again. So the connection doesn't have to be continuous. Web browsing is not a service, it's not an application which needs to be continuous. So that's why most of the applications we use, they can tolerate all these breaks, that you break a connection and you make a new connection. That's why this has not been very popular. In order to modify the internet infrastructure is very difficult. Any technology which has been introduced, if you look at the history, any technology which has been introduced which needs modifying the internet infrastructure, most of them have failed. Because the internet is so big, changing the infrastructure is extremely difficult. Unless there are few cases when they have succeeded. One is when companies can make money out of it, and there's a real need for that sort of service or technology. And I can give you, I can talk to you offline that a lot of technologies which have not succeeded just because you need to change the internet infrastructure. And the other issue is there is a high handoff latency when you are handing off between these networks. When you're handing off between networks, there is a disconnection. So here you are connected to this home agent. When you are here, you are disconnected actually, because you are going to get the new IP address from here, and then tell the home agent that you're here, and there's a protocol running between these two. This takes time to set up. During that time, the packets which are coming here, either they have to be buffered here, or they are going to be lost. There are two ways to handle it. So amount of buffering, there's a limited amount of buffering you can do. After that, the buffers are going to overflow. Number one. Number two, if you are doing a real-time service, let's say you are doing interactive voice, then when you are handing off from one network to another network, if you buffer them, then that sort of service is not going to work because it's an interactive voice. So there is a high latency, and there is also loss because you are buffering and the buffers overflow. The inefficient routing path, this is very interesting that the path is very inefficient in the sense that if you are trying to send an email to me, I mean, look at the email. If you try to send an email to me at my email address edu, from here is going to US to my server, and I am fetching my email from the server in the US, although we are sitting next to each other, right? But we are going 5,000 miles there, and I'm going 5,000 miles to get it. So there's basically 10,000 miles the packets are flowing. We are sitting 10 feet away, right? So the path is very inefficient. It's 10,000 mile round trip where we are sitting 5 feet away. You might say, I don't care whether you give it directly to me or it goes 5,000, 10,000 miles. I don't care. I have not been caring. I understand because there's a lot of bandwidth available, so we don't care much. But if you are running interactive service, this is going to be an issue because this is long distance. I was trying to sync my files with my server in the US last night, and because of this, and it took so much time because of this distance, right? So distance sometimes matters. In some type of service, distance matters. If I'm talking to you, it might matter if it is long distance. So anyway, the routing path is very inefficient. There is conflict with network security in the sense that if I am a foreign network here and I'm trying to send packets to outside world using my IP address from Oklahoma, then your network might stop me because they might think that I'm a foreign guy here. I don't belong to this network. Otherwise, if I belong to this network, why is my source address not this address? So the network security solutions, they're going to stop my packets. So there is a conflict with network security solutions like ingress filtering. And then there are issues of servability and manageability because there is a server here. If this one fails, then I'm off the hook. Nobody can communicate with me. So that's one big issue also, that there is a home agent which I have to rely on. So those are some of the drawbacks of mobile IP. Doesn't mean that you cannot use it. You can still use it. There are a lot of services which will be running perfectly okay. But these are some of the issues which are known issues of mobile IP. So when we were trying to develop this handoff scheme for NASA, and they were working with mobile IP, and we said that we wrote a proposal saying that we are going to develop a handoff scheme which will do all the stuff mobile IP can do, and it will not have all those limitations. It will take away all those limitations. So that is the sort of proposal we came up with. And we are going to develop it ground up from the scratch. And so here was the motivation why we started this project, that there are a lot of projects at NASA which are considering using IP in space, and they were trying mobile IP to do the handoff and location management. And these are some of the projects. This measures the precipitation on Earth. This is how to work, how the nodes can be worked as, how the satellites can be considered as nodes in the internet. And then there is this project, and they are also working with Cisco on developing mobile router. That means a router which can actually move around. So these are some of the projects, which means that there is a lot of need for developing a scheme which would be similar to mobile IP, but it would be better than mobile IP. That's what the objective was. So eventually mobile IP is going to play a major role in various projects at NASA, and these are some of the projects. This is Advanced Aeronautics Project, and Weather Information and Communication Project, and the Small Aircraft Transportation. These are all going to use mobile IP, or that was the plan. So we wanted to develop an efficient protocol to do all this stuff, the mobile IP stuff. It has to be secure, of course, and the handoff would be preferably seamless, which means it can do the handoff with zero disconnection, seamless handoff, not like mobile IP where you have to break the connection, establish a new connection, and then restart the connection, which takes a long time. So we wanted to do it seamless. So the objective was, so there should be no new hardware or software for the internet, which has to be installed on the internet because it's almost impossible to change the internet. the handoff latency has to be low, the packet loss has to be low, the data path has to be efficient. So if you are communicating, if I'm communicating with you here, it doesn't have to go 10,000 miles. I should be able to communicate directly with you. That's one objective. Then you should be able to cooperate with the existing net security solutions. I should not be stopped because I'm a foreign guy here. I should be able to use the network. The survivability, scalability, all these issues which are in mobile IP, we want to mitigate those issues. We want to develop a protocol or a scheme which will remove all those problems we have in mobile IP. So the basic concept, how do we do it? I mean, we have to come up with some basic concept. What is the problem with mobile IP due to which we have all those problems? So we found that the basic problem is the location management and the handoff. They are actually coupled together in mobile IP. Mobile IP considers location management, that means finding out where you are. And handoff means going from one tower to another tower, or one base station to another base station. They are tied together in mobile IP. How do they do it? They basically do it by the home agent. The home agent keeps tracks of you, where you are, and also does the handoff at the same time. So in order to solve this, we said, okay, if we decouple this, if we make these two independent, then might be all those issues will go away. And so we wanted to find out, we wanted to do location management and handoff in parallel at the same time to data transmission. So we decouple those. Here it is done sequentially. You do the handoff first, and then you do the location management. So we want to decouple that and develop a scheme where we can do it in parallel. The other issue is we allow the layer whose performance is to be optimized to take responsibility of the handoff. If there is a layer whose performance you're trying to optimize, let's say you're trying to optimize the performance of the voice communication, or let's say the transport layer, how much data you can get is the objective of the transport layer. And handoff is done by different layers. So that layer cannot optimize the different layer because the networking layers are all they are layers, they are stacked. And you can change a layer without affecting the other layer. So if you are trying to optimize your handoff, you may not be too worried about other layers which are more worried about throughput. So those are actually decoupled. So we want to say that the layer whose performance you are trying to optimize, let that layer take care of take the responsibility of the handoff also. So that it has an interest that I need to do a handoff so that the performance is optimized. And the way we implemented our scheme, the thing we want to do is use multi-homing to achieve simultaneous communication with multiple access points. That was the thing we came up with, that if we want to do a handoff from tower to tower, mobile IP it breaks the connection, reestablishes, gets a new connection, new IP address, new IP connection, and then reestablishes a connection. So the basic principle is called break before make. That you break the connection before you make a new connection. So that is the mobile IP concept. So we wanted to say, we want to make the connection first before breaking the connection. We want to make the connection first before breaking it, so that we make it seamless. It's very simple in concept. That if you want to be seamless, you first make a new connection, then you break the old connection. And in order to do this, TCP and other protocols which are in common use, they cannot support this. Like TCP is an end-to-end connection where you cannot make a new connection with a new endpoint or the same endpoint. You cannot make a new connection before breaking it because TCP doesn't support two IP addresses at the same time. If you have a TCP connection, it is one IP address to one IP address. You cannot have one IP address to two IP addresses. You cannot have that, which means you cannot have a new connection added to your TCP connection before you break the old one. So we looked at which protocol can do it, and we found that there's a new protocol called Stream Control Transmission Protocol, and that's an internet standard. It's not in widespread use, but it's already there, it's standardized. That can actually do this sort of thing. The one we want to do is multi-homing. And if we use this protocol rather than TCP, then we can do multi-homing. In that case, we can do all those stuff. So where does TCP stand? HTTP stand? This is the networking protocol stack, physical layer, link layer, IP address, TCP, UDP, upper layer. So HTTP actually is here. So it's at the same layer as the TCP and UDP. and it's just another independent protocol, which has two main advantages over TCP. One is called the multi-homing. That means it can have two IP addresses at the same time. And the other is called multi-streaming. That means if you are downloading data, let's say you're downloading a web page, and there are 5 images. You can download the 5 images at the same time in parallel with 5 different streams, which TCP doesn't support. So in this particular project, we are exploiting the multi-homing feature of the HTTP. So to summarize, both of them are reliable transport protocols. The congestion control is very similar. The main strength of TCP, one of the big strengths of TCP is the congestion control and congestion avoidance. The whole internet works without congestion. The main reason is the congestion control is very, very rigorous. It's very strict in TCP. And the other thing is the IP layer, which is common layer for all networks. That has to be the same for every network. So IP layer actually glues together all the different networks, and TCP makes sure that there is no congestion and that sort of stuff. So these two protocols are very robust, and that's why the whole internet, I mean, if you visualize the internet, is a huge network. It works. And HTTP has all the good features of TCP. In addition to that, it has two new features. So we can pretty safely move into HTTP, knowing that it will not affect the internet, and knowing that it will have 2 new functionalities. And we can also use the multi-homing to do the handoff we want to do. So again, as I said, HTTP is a standard protocol. So we're not inventing HTTP. We're not developing new protocol which has to be tested. It's already tested. It's standardized by IETF. So, and it actually comes with Linux. If you get a Linux, you will find the HTTP protocol there. We don't use it. Why don't we use it? We don't need to use it. We are happy with TCP. So when we're happy with something, and when there's a new protocol which comes in, we don't use it because we don't need it, however good it is. A good example of that is IP version 6. IP version 6 is mature. It can connect, let's say, you can connect anything in the world, right? Because there's so much IP address. IPv4, which we use currently, we ran out of IP address long time back, and we came up with a ad hoc solution, and the solution was using NAT, network address translation. So you're behind your router, and you've got private addresses. So using NAT solved the problem of IP address shortage. Although we had IPv6, which solved the problem, but we still don't use IPv6 because we can still work with IPv4. So unless there's a need, it's very difficult to change anything in the internet. I mean, that's the lesson we learned over the years. Just because the internet is so big. So in this particular case, the HTTP is a standard, so we can use it. Now, I'll come to that question of why we're not using it. I mean, what is the issue if we start using it? Let me go to this one. So mobile IP, the concept of Sigma, which we are trying to develop, the basic concepts, is basically making a new connection before breaking the old connection. So when you're moving from one network to another network, you establish a new connection with a new tower, and then you tell your host, you tell your computer you're communicating with, that I've got a new IP address from here, so send everything to me through Poland. So if I'm in Poland, I get an IP address, I tell my friend, whoever is communicating with me, send all packets to this IP address in Poland so that I can get it directly. But mobile IP does it like this. It goes from here to my home network. In US, it comes to Poland and then to here. So in this case, I establish a new connection and then break the old connection. Now you might say, how do I make connection from US to Poland? This is too far, right? But we're not talking about that far. We're talking about between nearing places. So we keep on moving from tower to tower. So, so that was the concept we had. Concept-wise, very simple. Implementation-wise, it became very, very difficult. How to implement it? So we developed this concept, and multi-homing using HTTP supports this. So what HTTP does is, if you have a connection from here to here, you can get a new IP address. You can tell your host that I have a new IP address. The host starts communicating with you over this new route. then you tell this network that I'm not going to communicate with you anymore. So I break the connection. So my handoff is seamless. So that was the basic concept. So the advantage is reduced packet loss because we are making new connection before breaking it. The handoff latency, there is a handoff latency, but the user cannot see it. The user does not feel the handoff latency. That's a big advantage. The throughput is increased because we don't lose packets. There's no special requirement routers and access network. This is a very important thing, that here we are only, we are not telling the network to do anything. For example, when I'm here, I don't have to tell the network here that I have moved from somewhere else to here. So I don't have to tell them. I can do it myself. And I don't have to tell my home network that I'm moving somewhere else. So forward my packets. I don't have to do that. So the way it's going to do is I'm going to tell the one I'm communicating with directly, I tell the other host directly that I'm here, use my new IP address. And the packets will come straight to me through this new IP address. And again, why TCP cannot do it? Because I cannot put a new IP address without breaking this one. But HTTP does multi-homing, so it allows me to do that. So we implemented this. So now, where does it come from? When we were looking at previously, all used to look like satellites, I was showing you. But now there's no satellite business here. There's all people and look like phone, and then there's a computer here. So if you look at this one, you can think of this one as a satellite, which is sending data. This one is a ground station, and this one is a ground station. So this person is moving with the mobile device, which is like a satellite, which is moving with devices which are collecting data. These are telescopes and other devices which they have on satellites. And these are ground stations. So when a satellite moves from one ground station to another ground station, it first establishes connection before breaking the old one. And we are using the HTTP. So we developed this scheme. These are all in our papers in details. Now, the way mission agencies work is if you write a paper and publish it and get a best paper award, is very good. But how does it work with our system? That's the engineering part. So we wanted to, the way these agencies work is called technology readiness level, that you have to move from one technology readiness level to another one before it can be implemented. So if you want to implement something in space, there are, I think, 8 or 9 levels you have to cross. And the first, so the first level is you have to show it on paper that it works. Then you have to do simulation in the lab. Then you go one level up and also experiment in the lab. And then the next technology readiness level, TRL, you have to show that it works in the lab, but in an environment which is the real environment. But still you're doing it in the lab. So you move up one technology readiness level, TRL. Once you've done that, you have to move to the next level, which is you have to show in an experimental network down in your lab, but it has all the environment in which it's going to be implemented. And then, so what we wanted, so we went through all these levels, simulation and then lab experiments and all this stuff. And then we want to implement on a real satellite. And before that, we have to implement it on a hardware which is running in the satellite, but which is in our lab. So basically, you have to get a satellite in the lab and then experiment with it and implement it there before you can actually deploy it up in the space. Because these mission agencies, you cannot just go and deploy something in the space, right? And if something goes wrong, satellite goes somewhere else, right? Or communication breaks. Or if you are implementing something for the Air Force or the military, right? You cannot just implement there in the warfield. I mean, you have to go through many, many levels of testing. And those are the levels they call it, called technology readiness level. So the bottleneck, one of the bottleneck was when we wanted to implement it in the satellite, and the hardware we were using was the, the company is called Surrey Satellite Technologies Limited. This is in Surrey in England. And this is the board, it's called a solid state data recorder. That's basically a single board computer which is up in the satellite. So we had a copy of this in the lab, in the NASA lab. And we're trying to implement whatever we did here on this piece of hardware, on this piece of board. Now, when we developed this, we're using Linux workstations, state-of-the-art computers with how many cores? Multi-cores, 4, 5, 8 cores, and all the stuff, right? We developed the scheme, simulation, experiment, everything works smooth. When we want to implement it here, they said, oh, the memory is not 8 gig. The memory is only 256 meg, right? And there's no HTTP, there's nothing there. right? How do you implement it? So, and the processor is very old, so it's not the state-of-the-art processor, because if you go into the real field and see what they have implemented, space-wise, or if you want to look at the army, what they're using, these are very old technologies. Why are they old? Because they have been very well tested. New technologies are being tested. You cannot deploy something in the real world which you are experimenting. You cannot get a blue screen. You cannot say, you cannot have it in a real environment. You cannot afford all those. You can afford to use a very old system which works perfectly, right? So when we want to implement it here, we found that there is no networking stack, there is nothing, there is no fast processor, there is no memory. Memory is very limited. So porting the stuff we did into this board was a nightmare. I mean, developing all the nice schemes which you see in the paper was very easy as compared to what we had implementing it here. So we had to take the STTP stack and remove every component of it which is not required, and use a bare minimum. So for example, in STTP, we have to remove the multi-streaming part because we don't need it. Anyway, just to tell you about the real-world issues. So eventually, so that is the sort of environment you are up against when you are doing applied research and you want to implement in a real mission. Like for the army or for the space agency or something, you are up into a lot of real-world issues. All right, so the way, so the signal signaling procedure is like this, coming back to where we are for the handout. So we have a satellite here, we have a ground station, we have a scientist here who is going to download the data from here. The satellite obtains a new IP address in the new domain, which is from here, gets new IP address when it gets in touch with the new ground station. And then the satellite notifies this scientist that from now on, please communicate with my IP address through this ground station. And then the satellite, sorry. Okay, the satellite has a remote computer set. So, let me go back. So here, so there is new communication. The satellite lets the remote computer set primary address. So once you tell this one is going to set this person is going to set this IP address which the satellite has as the primary path, because previously this was the primary path. And then we have to have an update. We have to have a location manager. So there's a location manager here. So the satellite gets a new IP address from here and tells this location manager that I am actually with this new IP address. So that's the location manager. Again, you might say, where is the location manager? This is something you have to do to change the internet. So we did not actually put a new location manager, but we use a DNS as the location manager, and I'll tell you how we did that. So again, if you remember that we are not trying to just develop a new location management or new handoff scheme. We are up against a lot of restrictions, a lot of constraints that what we have to do. We have to do something without changing the internet infrastructure. That's one of the big things we are up against, that we cannot change the internet infrastructure. Then once you are out of touch with the old ground station, you deactivate the old IP. You say that, okay, I don't have the IP address anymore. So you tell the user that delete the IP address which I had earlier. Always communicate with me through the new IP address. So let me pause there for a second. If there are any questions, should I keep going?
We have about 5 minutes.
Okay.
If you don't mind.
Okay. So one technology we used for this one was a vertical handoff, which means you hand off from different technologies. Like in the building, you have Wi-Fi. If you step out of the building, you have cellular connection. And if you go further out into the ocean or mountain, then you have the satellite connection. So what we want to do is have a seamless connection when you're moving out from the building to the outside to the satellite. Everything is seamless. And this is called vertical handoff because you are handing off from technology to technology, from different technologies, Wi-Fi to cellular to satellite. And there are a lot of applications for this vertical handoff. One of them is the healthcare application. In order to do this, so we developed a scheme, or we modified the Sigma to do the vertical handoff. And we did the vertical handoff from wireless LAN to Sprint cellular network, and from Sprint we can also go to the satellite network. And it was a very nice demonstration that we were running a video on our laptop inside the building using Wi-Fi, and we stayed out of the building. It automatically connected to the Sprint first, and then disconnected from the Wi-Fi. So our video was running smooth and nobody could detect that we are running, we are actually handing off. Except that the video degraded in quality because the screen could not support the bandwidth the Wi-Fi could, but the handoff was very smooth. So that was the experimental testbed. That was very initial one we did in the lab to show that the Sigma testbed is going to be, or Sigma handoff is going to be much better than the mobile IP. So this was the Sigma testbed inside in the lab with laptops and access points and using the production network. So using the university's production network to do the handoff without telling the university. That was one of the things, that we can do a handoff without letting the network managers know, or even telling that we want to do a handoff. So this was the mobile IP testbed, which is a standard testbed for mobile IP. I think the interesting part was here, if you look at the throughput, the amount of data we're receiving from the server versus time, that's how the data was received at the mobile host. And you might say that the data fluctuates. Yes, the data fluctuates because we're running in a real environment, and these are because of congestion control. So the network is congested at different times, so the amount of throughput you get is not uniform. They always fluctuate with time. But if I asked you where did the handoff take place, you would have no clue where the handoff took place because the data communication is continuous. But from experiments, we know that the handoff took place here during this time, the red zone. But if you look at that, the throughput did not drop at all. It just kept continuous. All these drops are due to congestion in the network, not because of handoff. We use mobile IP, and if you do mobile IP, then of course you can see the throughput completely dropped here. And that was when the handoff was taking place. And that was about, how many seconds? 40, 20, about 8 to 10 seconds. Right? So there was no connection for 8 to 10 seconds. That was quite a long bit of time. 10 seconds of no connection, or 8 seconds of no connection. Whereas we had in this one, we could not even tell where the handoff was. So what was the trick? The trick was to make a new connection before breaking the old one. And in order to do that, we have to use HTTP. So you might say that, but HTTP is not used by applications, right? Skype does not use HTTP. None of the applications use HTTP. How can you run your scheme when nobody uses it? You have to change all the applications. This is very true. You have to change all the applications. You have to change all the TCP calls to HTTP calls and recompile those applications. But nobody's going to do that. So why is it useful? It's useful because we are doing it for a particular purpose, a space agency. And for those ones, we can just customize it. So those few computers and those few equipments up in the sky, we can always recompile those few applications which are used in the space. So it's a smaller area of applications, and we can recompile those for HTTP. So, and they will still work. So this is a narrow area of work we are saying, but it's going to be very efficient. That's what we're trying to develop. Network mobility is another thing which can be adapted. Our scheme can be adapted to this. So basically saying that if you are on an aircraft and you are a lot of devices and you can always communicate with the internet individually, rather than doing that, what is done is done in aggregated way. Aggregated way means, this is very interesting that, so there is this internet and there is this network with a mobile router. So let's say this is a plane, and the plane has a mobile router in the cockpit. There are devices in the cockpit which are connected to the mobile router, and then it accesses the internet. And then when you are, so this is your device, and you jump on the plane and you connect to the mobile router in the plane. That's what we do when you connect to the Wi-Fi in the plane. You can have your own network, personal area network with your own mobile router and your own devices, which a lot of people carry now, their own router. You can connect your mobile router. You can connect your mobile router, personal mobile router, to the mobile router in the plane, and then the plane starts moving. So all the thing that happens is this mobile router in the plane actually hands off to new access point, and these devices are not aware of this handoff. And we can do this using this mobile IP concept, but we can also do it with this is called the network mobility, and we can also implement it with the. Let me skip this few slides which are detailed. So we can also change the sigma we develop and do the same sort of mobility for networks, and we call it Cinema. It's basically the same concept, except that there's a mobile router, and this is a mobile network, and the mobile router will take care of the handoff from one base station to another base station, so other devices in the network, the mobile network, they're not going to be aware of the handoff going on. So the mobile router will take care of the handoff. So this is useful for airplanes or buses or ships or where a network is there and it's moving, or a train. It's very useful for that sort of applications. Going to skip the details. So a comparison between the industry standard NEMO and the one we developed. One of them is space network suitability. Both of them are suitable, the one we developed and the one which is industry standard. Both of them are suitable. But packet loss is very low in our case, is very high in the other one. Our one is very efficient because we use direct route, mobile IP or the NEMO, which is not very efficient. So there are a lot of advantages in our scheme, because the reason is we wanted to optimize for all of these, and we really achieved, we really optimized all of those parameters. So to conclude, the NEMO BSP, which is industry standard, had a lot of signaling for nested mobility. Our scheme, which is based on IP diversity, that means you can have multiple IP addresses on the same device and you can use all of them at the same time. See, you might say that my iPhone has IP address from the Wi-Fi and also IP address from Orange, right? Also, my phone has an IP address from Orange and also from Wi-Fi, right? But remember that we're not using both at the same time. We cannot use both at the same time. So what we're saying here is, the scheme we developed, you can use both of them at the same time in order to increase performance. That is the beauty of this, that you can use everything which is available at the same time, multiple IP addresses. And also when you're doing the handoff, since you're already using Orange inside the building, when you go outside the room, outside this building, you're already connected there, you're already communicating. All you need to do is when you use a Wi-Fi connection, or move all your traffic over Orange. That's all you need to do. Also our scheme avoids packet encapsulation, use optimal route, all the advantages we wanted to have. We developed the Cinemo and the Sigma, and we found that it has all the advantages, of course, because we wanted to develop a scheme which has all those advantages. A lot of people have worked on it, and I need to thank all of them, and also NASA, which funded all this project, and Cisco also funded this project. And a bit of sales pitch. I'm the editor-in-chief of 2 journals. If you have good papers, excellent quality papers, which will attract a lot of citations, please feel free to submit. What is it called? Jian Kui, right? Thank you very much.
Well, I think we can afford a couple of quick questions only. I am sure there are lots of communications people in here. Not me, so if you rely on me asking a question, I can only ask you to establish a mobile seamless connection to lunch. So, what questions do we have? Yes.
Actually, it's not a question, but a comment. Have you? There is a lot of need for similar solutions for the FAA. This next gen system that is supporting the new way how the air traffic management is going. Requires this kind of a connection. Satellite communication is one of those. Have you tried to also to do this with the in relation with the Federal Aviation Administration? Because I know that most of your work is done with NASA.
Yeah, we have not actually worked with FAA. In order to work with them, actually we need some sort of contract or grant, but and yeah, I haven't actually worked with them, but it's a good point.
Okay, then we can take it off.
Sure. Thank you.
Okay, any other question?
When is lunch?
Yeah, you are hungry, obviously you are hungry. All right, so thank you very much. Thank you for